Applications of differentiation. We are going to look at, we shall cover all these tangents and normals, stationary points, have sketching 1, maxima and minima. These three are closely related, these ones here. Then rates of change, parametric equations, trigonometric functions, though we have done some numbers involving differentiation of trigonometric functions, but we shall go into details. Then small changes, inverse trigonometric functions, then logarithmic and exponential functions. That is what we shall cover. So, what we shall find in tangents and normals. A tangent is just, if I have a given curve in its form, a tangent is that line which will cut off at a point which tends to be straight. If this is my x and this is my y axis, or this is the y and this is the x, sorry. A curve will, if a curve is tending to cut off at a line cuts off a curve at a given point, that is what we call a tangent. Then a normal is just that line that is perpendicular to the tangent. So a normal is perpendicular to the tangent. When you look at what we started with, we said that when you differentiate, you get dy x. Say this is our curve y is equal to x to the power n. And we say that our dy x is simply going to be n x to the power n minus 1. So if you have, this is the gradient function for the whole of this curve. But now if you just choose off at a point where this tangent meets the curve, we have to get the values. Our previous video has shown we can locate the exact value where the gradient we want is located. For example, if the point here is 1, 1, you just come and substitute for the value of 1 and 1, you get the gradient. So we know that this is the gradient function, which we can also refer to as the tangent, the gradient of the tangent at that point, which gradient is noted as m. We can call it, say, m1. Now, for us to be important to get the normal, we simply get the product of m1, m2. The product is always equal to -1. This is geometry. In the future, we shall see how this one comes about. So, m1 times m is equal to -1. This implies that the gradient of m2 is simply the negative reciprocal of our function, our dy(x), which I would say we apply. So that is what we're going to find in the tangents and normals. So we can easily get the equation of the tangent, having been given the curve. We can get the equation of the tangent because we have the point at which the curve is meeting the tangent. We can get the gradient at that point, then we get the line passing through that point. Then we can also get the equation of the normal, still through that same point, but now the gradient of the normal is going to be, this is the normal, gradient of the normal is going to be just a negative reciprocal of the gradient of the tangent. So that is what we shall find in the tangent and normals. Then stationary points. For stationary points, our curve can either have, this is 2 here. If we have our graph like this, we can have something coming like that, then we have something like this, then we can have something like that. So our curve can have the maximum point, it can have the minimum point, then it can also have the point of inflection, where the curve tends to change route, but it doesn't change in a given way. Like clearly we see minimum and maximum. So it can either be this, or it can be, we have it like that, or we can also have it going in this direction. We have it like this or like this. So this is a point of, this is referred to as a point of inflection. Let me just write it as, we refer to as the point of inflection. So These are the stationary points. We have the turning points, maximum and minimum. Then we have the point of inflection, which can be represented like this or like that. That is what we shall find. But what we should take note of, that for stationary points, since the curve is changing course, the one that has been increasing now starts to decrease. If this was a plus, this is now becoming a minus. And if this is a minus, now this is becoming a plus. So from plus to minus it gives a maximum, from minus to plus it gives a minimum. We can easily notice that this one happens at a point whereby our dy x is equal to 0. We shall see why is it equal to 0. Then, having established stationary points, we can be able to differentiate between them. Is it a maximum? Is it a minimum? Is it a point of inflection? So that one would be seen as we are doing the curve, sketching one part. So if we are sketching the curve, we shall be in motion to tell that, okay, this is the maximum, now this is the minimum on the curve, then that's the point of inflection. Then also, when we proceed to maximum and minimum, still maximum and minimum, they are closely related. Like I told you, these three are closely related. So we need to know that at maximum or minimum point, our dy x is equal to 0. So everything we do to get that value, of which the value they are talking about of x is maximum, minimum, this is the principle we shall use. In case it is area, we shall have the a. For example, if it is the ax, this will also have to be in 0. If they are talking of the volume, still that the v, say the r, must be equal to 0, depending on the example we have. So these three are closely related, they move hand in hand. What governs them is at that point where there is the maximum, minimum, or turning point, the gradient is 0. And then the rates of change, these ones are seen so much into these figures. For example, the cone, we can see them in the cylinders. So here examples will do us very good, but we should know that we have some things that we deal with, dv dt, we shall have dv dr, then we shall also have the a dt, depending on which figure they have given us. And then this is the application of differentiation. Then we can also have the r and t, which combines most of them, and so on and so forth. So these ones, we shall be using a lot of chain rule here. If you have issues with chain rule, you can first go back and list the video of chain rule. Chain rule will help us here in rates of change. We cannot go without using chain rule. Then parametric equations, we saw different equations. We saw the implicit, we saw the explicit, but now we have the parametric equations. Parametric equations are mainly into x, say x is expressed in a given parameter, say 2p, then also y is expressed in another parameter, say 1 over p squared, something like that. So these are parametric equations whereby we can get the dy dx, but still getting the dy dx of these parametric equations, we shall need to use the chain rule. So chain rule is also going to come back here. Parametric equations. In parametric equations, the only tricky thing is when they ask you to find the second derivative, the squared dy dx is squared. But we shall have a small hint of second derivative as we look at stationary points, because we shall need to establish the nature of the stationary points. So we shall have a small hint on the second derivative. But when you look at the parametric equations, the second derivative is a little bit different, totally different. Trigonometric functions, these ones all know are the common ones: sine x, cos x, tan x, then they are reciprocals. We shall see when you differentiate a sign what you get here. Those are not so hard for us. They will not bother us so much. Maybe what changes in case they have given us, say, maybe sine 5x, or they have given us sine maybe power 6, 6x. but it will be the same model we use. Still, these ones require us to use chain rule. So chain rule is going to come back here in case we are to do these numbers, which are a little bit complicated on the right hand side there. Then small changes, we shall apply small changes in different ways, getting the square roots of values, the cube roots of values. In case a person gives you something like that, in case a person has given you, get the square root of say 98, these are small changes we shall use. Then also we can apply small changes when we are dealing with given perimeters, areas around a given figure. Small changes will come in case you're dealing with a circle and the person wants to get percentage errors or the percentage error and so on. We shall look at small changes coming in. Then inverse trigonometric functions. We have trig functions. These ones we have written down here. Sine, cos, and tan. So inverse trigonometric functions, we just get the inverse of sine x, which is sine up of x. This is cos up of x. How can we differentiate them? Then, but if I need to get the cot up of x, how can I differentiate that? Still, we shall see that. Then finally, logarithmic and exponential functions. We shall also look at how to apply our differentiation in logarithmic and exponential functions, which logarithmic functions are just resembling something like this. If you have log of, say, I have log of this, maybe it's x squared, write it as. I have log of say x, and I have something like y squared is equal to 2x. How can I differentiate something like that? Then, how can I give you the exponential functions? The person has given me, this is exponential cos x. A person has given me x, and the power sine x. All these are exponential functions which we shall look at. So, for today, that's it for now.